Okay, students, so lesson 4.4, second derivatives and concavity, and we're going to start straight away with the task that you can see right here. What I want you to do is, in your workbook or on a spare piece of paper, I want you to consider the function y equals 4x cubed minus x to the power 4, and I want you to analyze it and then sketch it as best you can, labeling any points of interest. Give yourselves a couple of minutes to do that. Okay, so this is my second run at this video. I've messed it up once already, and so you'll see my notes are partially completed. We're going to do it slightly different from normal. So the first thing I'm going to do is run you through my thinking as a solution to this problem. So here is the equation y equals 4x cubed minus x to the power 4. I'm going to do 3 steps of analysis before I start my sketch, and this is what I'd really be expecting you to do. So the first thing I'm going to do is factorize, and using factorization, I'm going to identify what those x-intercepts are, and I find them at x equals 0 and x equals 4. And then the next thing I'm going to look at is stationary points. So I differentiate and factorize my derivative, so that I can see that dy by dx equals 0 at 2 places, when x equals 0 or x equals 3. And what I've just filled in here is the y coordinates that go alongside those, so I can see the coordinates of those stationary points. Okay. Then the third bit of analysis that I would expect to see from you already is then to start to look at, well, what happens as x tends to infinity and x tends to minus infinity. If we imagine x getting larger and larger and being positive, then y is going to become negative because the larger term is x to the power 4, which is going to dominate as x gets bigger and bigger. So y tends to negative infinity. And then if we think about, well, what about when x is negative and getting really large? Well, if x is negative and getting really large, both these terms are negative, and so in fact it's going to tend to negative infinity, and if anything, even faster, 2 arrows, than when x is positive. So using all this information and putting it into a graph, I end up with something that looks a little bit like this. There's really no other way it could be. The first thing I did was I drew my x-intercepts, and then I drew just a small horizontal line segment at the 2 stationary points with coordinates 0, 0 and 327 that I found earlier. And then I knew that I must have the curves going in these directions, finishing in the bottom left quadrant and the bottom right quadrant, meaning that there really isn't anything for the graph to do apart from what I've got here. Now, in today's lesson, what we're going to do is take this kind of analysis even further by looking at second derivatives. So you'll know when we got up to the point in the lesson where I was up to previously, because you'll see that I'll start writing rather than just uncovering the notes. But this idea of a second derivative we're going to consider to begin with. And the second derivative is f double dash of x, or d2y by dx squared. That tells us the rate of change of the first derivative. So the rate of change of the rate of change, as it were. And what we could look at is that, well, if this is positive, if the second derivative is positive, what that tells us is that the gradient is increasing, or in other words, the graph is getting steeper. The gradient is getting bigger. And conversely, if d2y by dx squared is negative, well, then that tells us that the graph is getting less steep because the gradient is getting smaller. So, with that in mind, I want you to get stuck in to the first 2 examples here, this one and the one at the bottom of the page. Give yourself 3 or 4 minutes and see if you can complete both of these. Okay, so going through the first question to begin with, what I do is, first of all, I differentiate. It's an exponential, so I just move the coefficient of x in front. F dash equals 2e to the power 2x. I do that again to find the second derivative, and that's 4e to the power 2x. And then I substitute in 0, which gives me a second derivative of 4. And really, that's the answer I would expect from all you guys. But what I've done here is just analyze that a little bit more using the information above. So the second derivative here is obviously greater than 0, and what that tells us is the graph is getting steeper. And that's something we know about exponential graphs. We know they get steeper and steeper. But I just want you to consider the fact that actually, as I continue this process with this function or any exponential function, the rate of change of the rate of change is always going to be positive, and it's going to just get bigger and bigger as we continue to do this. So in other words, as x tends to infinity, the function tends to infinity, the derivative tends to infinity, the second derivative, 2 dashes there, tends to infinity, the third derivative tends to infinity, etc. So all rates of change are accelerating. So not only is this function heading towards infinity as x or time increases, but it's getting steeper and steeper and steeper and steeper, and the rate at which it's getting steeper is also increasing. And at a time of pandemic, maybe there's no better time to reflect on how scary exponential functions can be when we know that they have these properties that they can get out of control so very quickly based on this mathematical behavior. Okay. The second example was slightly different type of function with y equals cos of 2x. And what they're actually asking us to do is to fit that and show that it is a solution to this differential equation here. We're going to touch upon differential equations more in coming units, but we can see that this is an equation that involves the first derivative and the second derivative. And so our first step would be to, looking on the left-hand side here, to write y equals cos of 2x, to differentiate it once to get minus 2 sine of 2x, to differentiate it again to get d2y by dx squared being minus 4 cos of 2x, and then to substitute those into the equation that they give us on the left-hand side. So here I've written on the left-hand side is dy by dx squared plus a quarter of d2y by dx squared, and substituting in, giving me 4 times sine squared plus 4 times cos squared. And what we just need to appreciate is that because this is a show that question, I'm going to do everything I can to show that I've done the work here. And so I'm going to put in this extra line equals 4 times sine squared plus cos squared, which we know is equal to 1. And so this is equal to the right-hand side as required. So hopefully okay so far. What we're going to do now is just revisit that first function and look at it in a little bit more detail. So here, the sketch that matches the one I gave you of f of x equals 4x cubed minus x to the power 4. And then what I've done here is I've just found the first and second derivatives and factorized those. And we're going to look at the relationship between these two graphs. So looking at f dash of x first. Anywhere there is a stationary point of f of x, we know that this must give us a 0. And in fact, we can see that happens when x equals 0 and x equals 3. We can see we have an x-intercept at those 2 points. Then to look at stationary points, we look at the derivative of this function, which we have here. And we see that the derivative is equal to 0 when x equals 0, when x equals 2, which gives me 2 stationary points. And to work out the y-coordinate here, I substitute in x equals 2 to the first derivative, and I think it gives me 16. So we have a stationary point at 2 at 16. And then what we can do with this derivative function is we can analyze it in the same way as we did previously by thinking, well, what happens when x is negative and gets really big, and what happens when it's positive and gets really big. And what we can actually see is if it's negative, then overall the gradient function is positive, so y is going to be up here. Whereas if x is positive, because of this term, overall the gradient is going to be negative, so we're going to be down here. And so our function must look like, cannot look anything other than this. Applying similar kind of trick over here, we look at our zeros first of all. We still have this 0 at x equals 0, and we have another one at x equals 2, and that corresponds to the stationary point of the previous graph. And at this point, because I'm looking at a quadratic, I am feeling pretty comfortable about this. I know it's symmetrical, so there must be a stationary point here. I could also find that by differentiating again. And I know a parabola with a negative coefficient of x squared must look like so. So maybe the only thing to do is to find the coordinates of this stationary point. The x-coordinate must be 1 because of symmetry. And the y-coordinate, if I substitute in 1 here, I get 12 times 1, so it must be 12. So these three graphs are obviously all related. We have f of x, we have the gradient function f dash of x, and then we have the second derivative. So to break it out a little bit, f of x has a maximum at 327. And if we look at that point x equals 3 over here, we can see that the gradient is equal to 0. And of course we know the gradient is equal to 0 at all stationary points, maximums, minimums. If we look at f double dash of x at x equal to 3, it's a negative value. We're down here, so it's less than 0. And we should be familiar with the fact that that tells us it's a maximum. The graph is getting less steep, so at that point it is turning a corner, going from positive to negative. The other interesting point on the original function here is 0, 0, and we call this a point of inflection, and it's stationary because at that point the gradient is 0. So dy by dx equals 0, we can see that here, this point on the gradient function, and f dash of x is also equal to 0. And that is another property of points of inflection, that where they're stationary, f double dash of x equals 0. Finally, there is a third interesting point here, and congratulations if you found this right at the start, that we have a point of inflection going on right in the middle here, or not quite at the middle, at 2 and 16. At this point of inflection, it is where the gradient is non-zero. So the gradient is 16 here. But f double dash is equal to 0. So if I substitute in x equals 2 to the second derivative, it gives me a 0 value. So what this means is at that point, the gradient for that instant is not changing. And that's because the gradient is moving from, the second derivative is moving from being positive, as in the graph is getting steeper, to being negative, the graph is getting less steep. And to do that, it must go through a specific point at this point of inflection where the gradient is stable and steady. And that happens when x equals 2. So I'm going to put some words to these things. Looking at the point 1 in between x equals 0 and 2 for this same function, we can see that the graph is curving upwards. And our name for that is concave up. It's curving upwards, like so. But if we go in between 2 and 3, so approaching, having moved past the point of inflection and moving towards the maximum, the graph is now curving downwards, and we call that concave down. Whereas at the point x equals 2, right in between them, it is neither curving up or curving down. It is stable, and so we say that that is a point of inflection, where we're moving from concave up to concave down, and the concavity is changing. Now, final note at the bottom. My way of remembering is always, and actually the notation is slightly different in the UK, they talk about concave and convex, but if you want to remember which one's concave up and which one's concave down, just imagine someone sitting in the cave. Concave up, the cave is facing upwards. Concave down, the cave is facing down. And that is always true. So, what I'd like you to do now is flip over the final page, and we're actually going to fill out a table which should be helpful for you when you're completing the exercises, and then also in your exam 2, because we're going to think about 9 different cases. We're going to think about what happens when either the gradient is positive, negative, or 0, and the second derivative is positive, negative, or 0. So pause the video and try and fill the table with all the options. And then I'm actually going to show you for this just one I did earlier. So, gradient being positive, the first thing I can draw in here is these tangent lines, because the tangent lines are have a positive gradient, so they must be going from bottom left to top right. Because those are tangent to the curve, that means that in the case where d2y by dx squared is less than 0, we must have the curve rising and concave down, whereas the points of inflection must come through that tangent, but they can bend in 2 directions, either moving from concave down to concave up, or concave up to concave down. Filling in the gaps down here, we have a very similar thing, but dy by dx is negative, so that means we're sloping down. This is a concave up function sloping down, this is a concave down function one sloping down, and then we have 2 options still for the point of inflections depending on which way we're moving. And then actually that extends also to the case where we have stationary points. So stationary points, when dy by dx is equal to 0, we can have a local minimum, a local maximum, or 2 different of stationary points of inflection. So, to clarify that just very quickly, what that means is that we've defined a point of inflection to be a point that occurs whenever the sign of the second derivative changes. So it is a point where the curve changes from concave up to concave down, or vice versa, and we've seen that in the table just above. And then it actually means we can apply a second derivative test to really any stationary point to tell us what kind of point it is. So if the first derivative is equal to 0 and the second derivative is positive, that means we must have a local minimum, and we know that because the curve is concave up. If the first derivative is 0 and the second derivative is less than 0, we must have a local maximum. Sorry, I've done these the wrong way. Here we go. Like so. And in the case where f dash is equal to 0, so the gradient is 0, then we actually need to investigate this a little bit further. And this is just something to be aware of, and we're going to look at an example in a second. It could tell us it's a stationary point of inflection. We know that stationary point inflections exist, and we know that they fit these criteria. But there are other options, because it could be what I would call an extreme stationary point. Because if we just think about this for a second, if the sorry, this should say the second derivative. If the second derivative is equal to 0, what that means is the gradient is not changing at that point. So it could be that the gradient is moving from positive to negative, or it could be that actually it's moving from positive to 0, and then it's going to move back up to positive again. And to think about what that looks like, we consider the graph of y equals x to the power 4 at x equals 0, and I've got that just here for you to look at. At this point here, we can differentiate twice and see that the second derivative is equal to 0, telling us we've got a stationary point, but it's not a point of inflection. It's what we could call like a bucket point, or an extreme stationary point. Because as we approach here, we have the gradient being 0, but then also the rate of change of the gradient being 0. So not only have we hit a minimum, but the gradient on either side of that minimum is barely changing at all. In other words, we have this very flat bottom, and of course it could also be a very flat maximum if we were to look at y equals minus x to the power 4. So we just have to be careful about these situations and analyze them further. So this is what I have finished off on the bottom of my notes here. And then the last thing I want you guys to do today is I actually want you to revisit the task that we looked at a couple of days ago, where you analysed f of x, f dash of x, and f double dash. I want you to go back to this. I want you to log in again, and hopefully now you'll see lots of problems that other people have set, and I want you to try and use your new skills to analyse those. So for example, here is a function that I'm going to set for all of you, where f of x equals 2 sine x plus cos of 2x. And what's going to happen if I click on graph it is it's going to show me 3 functions. One of those is f, one is f dash, and one is f double dash. And what you're going to have to do is you're going to have to decide which one is which. So I've given you a bit of a clue here because this one is previously labelled, but to do that, what I'm looking at is I'm looking at the maximums and minimums of each function, and then the points where y is equal to 0, because I know that the zeros of the derivative must correspond to the stationary points of the function, and the zeros of the second derivative must correspond to stationary points on the first derivative. So I want you to go back to this, have another look, and see if you can build your fluency with these type of questions. Then, as normal, complete the exercise and send me in your questions via the quiz. Okay. Best of luck. Speak soon.